I'm Jana Kuhn. I work with the alumni side with SSP, and we are so appreciative to hear from Wendy. If you wouldn't mind introducing yourself, and I'll turn the time over to you. But um, yeah, just introduce yourself. Let us know who you are and your history with SSP, all the good things.
Sure. Thank you. Hi, everybody. Welcome on this Sunday. It's afternoon for me, depending on where you are. It could be mid-afternoon, so I hope you're having a good weekend. I'm Dr. Wendy Bohon, and I am the branch chief for seismic hazards and earthquake engineering with the California Geological Survey. And today I'm going to talk to you about living with earthquakes and how the science can help to keep us safe when the earth shakes. And so I'm not nearly as interesting as the science, so I'm not going to talk too much about myself because that's no fun. We'll talk about what we're here to talk about. So I like to start. Hold on. Wait. This is the wrong one. I give a talk tomorrow too. I was like, you are not needing to understand this stuff. Hold on. Here we go. Yes. Someday I'm going to change around so I can see more than I always have this exact same slide for my cover because this is from the Ridgecrest earthquake in California in 2019. And I think it's such a beautiful picture. Anyway, let's get started. So I'm in California. And California is known for a lot of things, right? We have iconic cities, we have fantastic coastlines, unique ecosystems, beautiful mountains, and these beautiful beaches. I was just in Santa Cruz yesterday talking about tsunami hazards that we have in the state. But there's one thing in particular that California is really well known for, and that is earthquakes. And it is a well-earned reputation. So this is a map showing earthquakes in California in the last 30 days. But can you see my screen? It says my screen sharing is paused. Hello?
I can see it. Can others see it?
Do you see
Seeing
the
the world.
earthquakes on California? That is
It's
not
called
great.
it was called Seismic Hazard Map.
Yeah, okay, you guys, I'm so sorry. Here we go. Let me share the right thing, and then it'll be easier. Okay, let's
Oh,
go back.
That's it.
Here we go. Here's all the things I was just talking about so you can see them. Cities, coastlines, ecosystems, mountains, beaches, and earthquakes. Okay, here we are. So this is a map showing 30 days of earthquakes in California. We do not have the market on earthquakes, though. This is a map showing earthquakes in North America in the last 30 days. And so while you can see that the West Coast has the lion's share of earthquakes, and of course Alaska, which has more earthquakes than all of the West Coast combined, there are a smattering of earthquakes across all of the United States. And that's reflected in the USGS map showing the chance of damaging earthquake shaking in the next 100 years in the continental US. Hawaii is on here, Alaska's not on this map. So the areas that are in red, orange, and yellow are the areas that have a higher earthquake hazard, and the areas in blue and green have less of a chance of experiencing this damaging shaking. Now, population density is on this map in blues, in blacks and in purples. So why do we have such high hazard on the West Coast? So this is a map showing earthquakes around the world. Each of those flashes is an earthquake. And if you look carefully, you can see that they form a pattern. That pattern is showing us the outline of the tectonic plates because earthquakes are most likely to happen in the places where the tectonic plates come together. And in the US, that's along the West Coast. So let's look at the panel on the left-hand side and start at the bottom. Along the bottom there, we have the Pacific plate and the North American plate, and they're kind of pulling away from each other, and that's helping to open up the Gulf of California. So that's a divergent boundary. That slowly changes into a transform boundary as you move up into California. So one plate, the Pacific plate, is sliding past the North American plate, and that plate is headed up towards Alaska at about the rate that your fingernails grow. So California, not going to fall into the ocean. As you go up towards Cape Mendocino in California, that transform boundary turns into a subduction zone where this little plate called the Juan de Fuca plate is subducting or diving down beneath the North American plate. And so while that may seem complicated, it's actually even more complicated than that. So if we look on the right-hand side, this is a map showing the tectonic motions of the Western US. This is from UNAVCO, which is now called EarthScope. At the base of each one of these little arrows is a GPS or a GNSS station. So the arrow is showing the direction that the ground is moving in that location, and the length of the arrow is showing the fastness, like how quickly the ground is moving in that location. And so the thing I want you to notice about this is that many parts of the US are moving in different directions and they're moving at different speeds. And this is called differential motion, right? It's not moving the same way. And if you imagine you're on roller skates, okay? And one of your feet is moving faster and in kind of a different direction than your other foot, eventually your pants are going to split. Same thing with rocks. If you're moving fast or in different directions, eventually the rocks in between are going to break. And that is where we get faulting. How do we know where these faults are? Well, the GPS gives us one indication, but geologists are able to read clues from the landscape. This is called geomorphology. And we can look at the landscape and we can learn a lot about it. So I was in Palm Springs last week for the statewide California Earthquake Center meeting, and I was so excited on my flight back from Palm Springs to Sacramento because we flew right along the San Andreas Fault. Both of these images are pictures that I took of the San Andreas Fault from the plane. And so there's hints in the landscape that you can see. So the fault through here on the left-hand side, these are the San Bernardino, San Gabriel transverse ranges, right? Here's the fault right here. And then on the right-hand side, this is an image of the Carrizo Plain looking towards the southwest. That's the Temblor Range in the foreground. And if you're interested in learning the clues that geologists use to read faults in the landscape, I have some videos on that on my social media at Dr. Wendy Rocks. So you can go there and get a deep tutorial on how to figure out where the faults are from the air. But here is the San Andreas Fault in the Carrizo Plain. So the GPS can help us know where they are. Geologists can look at the ground and figure out where they are, but we also have additional tools that can help us. One of those is called LiDAR, light detection and ranging. This is an optical remote sensing technology that helps us to build three-dimensional maps of the ground surface. And so by having this laser scan back and forth, we get data that helps us to build these maps. They can do incredible things. So this is a LiDAR image of Northern California, and the San Andreas Fault is in this image. So this is work by Carol Prentice and others from the USGS. And let me orient you to what you're looking at. The knobbly stuff that looks like popcorn or carpet, those are trees. If you look down in the bottom left, it looks like the top of a heart. That's the ocean, and those are cliffs leading down to the ocean. Just above that, you can see a square. That's a fence line. And then above that, you can see a road running through here. The San Andreas Fault also runs through here, but it's underneath all of those pesky trees. So we can't see it to figure out exactly where it is. But using LiDAR, you can actually deforest an area, which means take the trees out, and you can see the ground beneath. Now, the resolution is not as high because we don't get as many laser hits on the ground in areas where you have vegetation. But just like sunlight filtering through the trees, you do get some, and that is enough for us to be able to determine exactly where the fault is. But don't worry, no trees are harmed in the making of these. We can put the trees back in and actually learn important information about the forest health. We can learn about things like canopy height, above ground biomass, and even in some cases, identify individual trees. So now we know where the faults are, but how do we learn about earthquakes that have happened on those faults in the past? In order to do that, we actually have to get down inside of the ground and look at the rocks. So to do that, we dig something called a paleoseismic trench, or a trench across the fault to look for ancient earthquakes, paleo-earthquakes, paleoseismology. So this is that same area in the Carrizo Plain that I showed you from the plane, only we're looking at it from a slightly different perspective. I want you to look at the orange image, which is one little tiny slice of this larger LiDAR image along the fault in the Carrizo Plain. There's those lines that are going across it. Those are paleoseismic trenches that we dug across the San Andreas Fault in order to look at the earthquake history of the fault. This is what they look like from the air. And this is what they look like from the ground. And so what we're doing is looking at the rocks themselves and figuring out where the layers are and how those layers have been disrupted or changed by past earthquakes. So we take pictures of the fault, and then we can actually map out the different layers. And there's some rules in geology that are important to understand in order to be able to read the rocks. One is that it's called the law of original horizontality. So when sedimentary rocks are deposited or laid down, they're laid down horizontally or pretty much horizontally. And there's the law of continuity. So they're continuous until they taper out on the edges. And if they are not horizontal or not continuous, then we know something has happened. And in this case, because we're in an active fault system, we know that something was faulting. So let's trace along these different layers. So if we look at the blue layer and follow it along, it is indeed not continuous. There are places where it's just completely gone, places where it's broken. The green one is the same. So these red lines that you can see right here that are vertical, those are actually areas where the ground was broken by past earthquakes. And in this part of the trench, we were able to see 4 paleo earthquakes. Now we can do things like carbon-14 dating, optically stimulated luminescence, or beryllium-10 dating in order to figure out the age of these rocks and the soils that they created. And that tells us about when these earthquakes happened. So then we can learn about the amount of time it was between each one of those earthquakes that happened. And that's how we get the recurrence interval, or the rate at which earthquakes happen. Now, this is an average, right? So you can say, on average, people get the flu, say, once every 5 years. Well, you could get the flu twice in a row. You could even get it twice in 2 years, but it's less likely. So this is an average. So when people say the fault is overdue, it's not really correct. It's more like the fault is ready. It's prepared, and it's, time to have an earthquake. So this tells us the recurrence interval, or about how often earthquakes happen on this part of the fault. But how do we know how big those earthquakes were? Well, the magnitude of an earthquake is dependent in part by the length of the fault that breaks during that earthquake. And so if we can figure out how many of these earthquakes we can find in different trenches, or how much of the fault broke, we can figure out about how big the earthquake was. So this is a map showing the San Andreas Fault and its sister fault, the San Jacinto Fault. Together, these two faults are helping to take up a lot of that motion between North America, the North American plate, and the Pacific plate as they slide past each other. Each of those triangles is a different paleoseismic trench. So we can see different earthquakes in all of these trenches, and then we can try and figure out which ones have the same date, thus which earthquakes broke what part of the fault, and that can tell us the magnitude. So by using paleoseismic trenching, we can figure out both the recurrence interval of different faults and the past magnitude of earthquakes of those faults. And that can give us an idea of when we might expect the next earthquake and how big those earthquakes can be. So I haven't even explained what an earthquake actually is. So let's talk about that. When we have those plates that are moving, right, they're moving very slowly, but they're building up stress and strain through time. Eventually, that stress is going to be stronger than the rocks, and they're going to move. That releases energy in the form of waves that we feel as shaking. And that shaking can do a lot of damage. So let's look at what can happen during ground shaking. So this is a CCTV footage from central Kathmandu during an earthquake that happened there in 2015. Something I want you to note is the square up in the corner there is showing the motion of a nearby GPS station that's recording the earthquake as the people are actually feeling the earthquake. So this is why we tell you to drop cover and hold on. You don't want to try and run around during an earthquake because you can fall and hurt yourself. Now, this video that I'm about to show you, just so you know, is showing really strong earthquake shaking from the magnitude 9.1 Tohoku-oki earthquake that happened in Japan in 2011. So this is from the Sendai airport. Shaking from this earthquake went on for more than 6 minutes. So ground shaking can cause a lot of damage. We think a lot about buildings being impacted, but it can also cause damage to infrastructure, things like roads, dams, and bridges. But there are other things that we need to consider when we think about earthquakes and earthquake impacts. The first one is liquefaction. So liquefaction happens in areas where you have soft sand and soil, a high water table, and the possibility for strong or moderate ground shaking. What happens is that the ground shaking pushes the water upward. That forces all of those loose grains of sand and dirt apart, causing the ground to lose strength. So it turns into almost quicksand. You know, I thought quicksand was going to feature in my life a lot when I used to watch Wile E. Coyote and cartoons, and this is really the only time that I think about quicksand. But liquefaction can be a problem, as it was during the 1906 earthquake in San Francisco. So this picture over here on the right-hand side is showing this house where the foundation actually sank into the ground due to liquefaction. There's also earthquake-induced landslides. So this happens when the strength of the hill slope material is overcome by the forces of gravity and the earthquake shaking. And for this to happen, you need steep slopes, weak geologic materials, and moderate to strong ground shaking. Tsunamis are often caused by underwater earthquakes on certain types of faults. Not every underwater fault causes an earthquake. Causes a tsunami. In order to have the tsunami, you have to have the ground move upward, which then pushes the water column above it upward, and then that flows out in all directions, causing a tsunami. So this is damage from that earthquake that happened in Japan in 2011, caused not only that massive earthquake, but also a huge damaging tsunami. And that tsunami impacted places all around the Pacific Basin, including in California. So this next video I'm going to show you is from Santa Cruz Harbor. There were $28 million worth of damage done in the Santa Cruz Harbor, more than $100 million in damage done across California from that tsunami that originated in Japan. So this feels significant, right? What should we do about this? What can we do to help mitigate the risks from earthquakes? Well, first thing that we need to do is realize that there is no such thing as a natural disaster. What we have are natural hazards that overlap with vulnerable human systems. There's nothing that we can do about earthquakes. That's just the earth doing earth things. What we do have control over are the vulnerability of our systems. How prepared are our populations to experience earthquakes? How strong are our structures? How ready are we for the earthquakes of the future? Unfortunately, we tend to learn geology the morning after the earthquake. So now I'm going to tell you a few stories about the earthquakes that have really changed California and how we've used those as learning experiences to try and help mitigate earthquake risk. So the first story starts in 1933 in Long Beach. It was the springtime. It was a Friday afternoon around 5:55. You know, kids are out of school. I'm sure people are doing what they're always doing around 5:55. We're ready to relax for the weekend, starting to get dinner ready, when suddenly a magnitude 6.4 earthquake happened on the Newport Inglewood Fault. Caused 123 deaths and about $40 to $50 million in damages. But frighteningly, the things that were very damaged were schools. So more than 70 schools around the Los Angeles area were completely destroyed. Can you imagine what would have happened if that earthquake had occurred 4 or 5 hours earlier when school was in session? It makes my blood run cold to think about it. And lawmakers didn't want to think about it either. So they almost immediately passed the FIELD Act, which regulates the design and construction of public school buildings to ensure seismic safety. And since the 1933 earthquake, not a single child or educator has died in a California public school due to an earthquake. And the California Geological Survey takes part in this through our essential facilities review. So all new public school building projects have to submit a geologic investigation report to CGS for review. And we check for things like surface fault rupture, earthquake shaking, liquefaction, landslides, anything that could compromise the geologic thing that could compromise the safety of that school building. But it's California, another day, another earthquake. This time it's 1971 in the San Fernando Valley. So this is an area near LA that's very populated, and it's also near the Sierra Madre Fault Zone. So it was morning time. This time people are just getting up, getting breakfast ready, when without warning, a magnitude 6.6 earthquake happened. Caused 64 deaths and $500 million in damages. Now, this particular earthquake was a little bit different because it broke the surface of the ground for about 12 kilometers. That's not like the Long Beach earthquake, which didn't actually break the surface. And so this caused a particular pattern of damage, and there were certain types of buildings that were really damaged during this earthquake, and those were hospitals. And so recognizing that hospitals are a nexus for community recovery, after this earthquake, they passed the Hospital Safety Act. So we also review hospitals the same way that we review schools. But there was the pattern of damage due to the breaking of the ground. And so recognizing that this was an issue, the California legislature passed the August-Priolo Fault Zoning Act, which says essentially that we cannot build structures intended for human habitation on the trace of an active fault. Very, very reasonable. And the California Geological Survey, in accordance with the August-Priolo Fault Zoning Act, maps active faults in California. The 1971 earthquake also caused us to create the Strong Motion Instrumentation Program. So this is a program that obtains vital earthquake shaking data that's used by the engineering and scientific communities, okay? We have more than 1,300 active stations with more than 10,000 sensors. 940 of those stations are on the ground, recording the motion of the ground, but we're also recording buildings, bridges, and dams. So we have more than 274 different kinds, 274 buildings, lots of different kinds of buildings that have been instrumented, more than 80 bridges, and over 25 dams. So now I'm going to show you a video of the Golden Gate Bridge. So we have more than 110 instruments just on the Golden Gate Bridge, monitoring the motion of the bridge. And what we're looking at here is shaking that occurred during the magnitude 6 South Napa earthquake that happened on August 20th, 2014. So this has been magnified 500 times so that we can actually see the shaking and the way that the bridge moved. Now on the bottom, it's showing you the scale. The blues are not moving at all or moving very little. And then as you get up into the warmer colors, that's where the bridge is moving more and more. And so there wasn't any damage to the bridge from this earthquake, thankfully. But what we can do with this information is give this shaking data to the people that are in charge of the bridge in order to determine whether or not the bridge is likely to have sustained damage by having shaking that was more than it was designed to handle, right? So you can really see it rocking and rolling right now. So this is one way that we can work together to ensure that our infrastructure is safe after earthquakes, and also to determine the areas where it's important for emergency responders to focus their efforts. Another day, another earthquake. This time it's 1989 and we're in the Bay Area. So this was not a normal day. This was an interesting day because it was the third game of the World Series and the Oakland A's were playing the San Francisco Giants in Candlestick Park. It was the Battle of the Bay, right? People were very excited about this game. Folks are heading home on their afternoon commute when a magnitude 6.9 earthquake happened on the San Andreas Fault. It started near Santa Cruz. So if you look down at the map, that star down there is showing the place where the earthquake started, and it ruptured or broke towards the north. Now, there's something really important about this map that I want to point out to you. This map is showing the shaking intensity from that earthquake. So every earthquake has one magnitude. That's the amount of energy that's released during the earthquake. But that earthquake can generate many different intensities of shaking in different places based on different things. So we'll go through a couple of those just briefly. One thing that impacts the intensity of shaking in a location is the magnitude of the earthquake, right? Larger earthquakes produce more shaking over a wider area. The second thing is how close a particular location is to where the earthquake occurred. So generally speaking, all other things being equal, the closer you are to the earthquake, the more shaking you're going to feel than places that are farther away. But the third thing is really important and is shown by this map. So the local rock and soil conditions make a huge difference in what you can experience during an earthquake. So in this map, the areas that are in orange, yellow, and red experienced higher levels of shaking, in some places even severe or violent shaking, whereas the areas in purple, blue, and green experienced less severe shaking. And so if we look at the distribution of shaking here, you can see that it's not necessarily concentrated right around where the earthquake happened. And that's because in the Bay Area, where you can see some of those reds and oranges, you have really soft sands and soils that can actually amplify the earthquake shaking. They shook harder and for a longer period of time. It's kind of like shaking a bowl full of Jell-O. Even after you've stopped shaking it, it's still going to keep wiggling. So if you look up near Oakland, you can see an area where you have kind of a higher intensity of red and orange. That is the area where the Nimitz Freeway collapsed. So even though it was relatively far away from the earthquake, there was a significant amount of damage that was done, and unfortunately, a lot of fatalities. So after the Loma Prieta earthquake, the legislature wanted to address things like liquefaction and earthquake-induced landslides. And so they passed the Seismic Hazards Mapping Act. And the Seismic Hazards Mapping Act directs the California Geological Survey to map areas that could potentially have earthquake-induced landslides and liquefaction. So what does that look like when we make these maps? This is a screenshot taken from an app I'll show you in just a minute that's showing these earthquake zones of required investigation. So the areas, the little narrow skinny zones of yellow, those are areas where there are active traces of faults, right? So that's the Aquas Priolo fault zone. And if you look down near Long Beach, that long skinny one close to the shore, that's actually the Newport Inglewood fault zone. That's the one that broke during the 1933 earthquake. The area in green that takes up most of the center of the screen, that's an area where you can have liquefaction. Again, that's soft sands and soils and a high water table. The areas in blue are the areas where you can have earthquake-induced landslides. Again, that requires steep slopes, weak geologic material, and strong shaking. So if you wanted to look at these, you can go to the EQ ZAP on our website, maps.conservation.ca.gov with all of the backslashes, or you can put in, California Geological Survey, earthquake maps, or earthquake zones of required investigation. And when you click OK and you go there, you can actually zoom in pretty close. So I just picked a random spot, zoomed in, and picked one parcel. So I clicked on that parcel, and when we look at it, what we see is that all or a portion of this parcel lies within an earthquake fault zone. This parcel is not within a liquefaction zone. All or a portion of this parcel lies within a landslide zone. And so this allows people that have businesses in these areas or live in these locations to understand what their hazard and risk are. You have to disclose this in your natural hazards disclosure when you're selling property. And for developers, land use planners, people like that, this helps to make really good decisions because a lot of these hazards can be mitigated. And so we can reduce our seismic risk by making sure that we are making good choices and using mitigation that is appropriate for the seismic hazard that we face in different places. But again, I talked a lot about California. Earthquakes are not just a California problem. They're not just a West Coast problem. We've had large earthquakes across the United States. And in fact, I'm doing a video series on earthquakes in all 50 states, and I am up to Kansas. So I'm going in alphabetical order, talking about important earthquakes in different states. So for instance, you see this bullseye over here in the mid-continent. That's because of this thing called the New Madrid Fault Zone. So there have been really large earthquakes in this area in the past, including several earthquakes that happened in 1811 and 1812 that were thought to be around a magnitude 7. They were felt widely across the East Coast and in the Midwest. Charleston, South Carolina has had a devastating earthquake in historical times. Mineral, Virginia had a magnitude 5.8 earthquake in 2011. Texas has magnitude 5 earthquakes regularly. So just about everywhere in the US can have earthquakes or feel shaking from earthquakes in adjacent states. So no matter where you live, it's important to know what to do when the ground shakes. The recommended safety action for earthquakes in the United States is to drop down to the ground, take cover underneath a sturdy object like a table, and hold on until all the shaking has stopped. And that's because when you're in the US, the most common way that you're likely to be injured is from things inside falling on you. So if you're outside, stay outside, move away from power lines, trees. Let's hope you're not near a cliff, move away from a cliff. You want to get away from things that can fall on you, and you want to make sure that you don't fall down because the ground can shake so violently that you're not able to keep your feet. So we want to make sure that you are safe from the main threats in the US. Now, if you're traveling outside of the US, you want to check in with the countries that you're going to see what their recommended protocols are, because for different types of construction, there will be different safety recommendations. So a great resource is called Shakeout. This is the world's largest earthquake drill. You can check them out at shakeout.org, and it is happening next month on October 16th. There are millions of people around the world that are taking part in this earthquake drill. So I encourage you to go check out shakeout.org. It has lots of information about how to be earthquake safe, information about earthquakes in different states and different countries. And then, you can register to do shakeout. So if you have any additional questions, I can take those now. And again, you can find me on social media at Dr. Wendy Rocks, and the California Geological Survey is at CAGO Survey across different social media platforms. So let me stop sharing. I was worried I was going to run out of time, so I think I did okay.
No, that's perfect. Thank you so much. If anyone has any questions, you can drop them in the chat, or you can unmute yourself, whatever you're comfortable with.
This is Bruce Rogers. I'd like to ask a question.
Sure.
Okay, Dr. Bowen, with all the computing power that we have, is anyone trying to map or model, model seismic, the tectonic plates using spherical coordinates? Is anybody trying to do that? Because obviously you were showing the movement of the plates in 2 dimensions, but can we do a 3-dimensional now of movement of the plates with the computing power that we have?
Absolutely. So we do that. We can actually do better and sort of do 4D. So we can go back in time, we can go forward in time. We can actually model down all the way to the core mantle boundary. And so there's some really cool technology that we have now called seismic tomography that actually allows us to not just see what's on the surface, but actually look at things underneath the ground by looking at changes in density and temperature. This is wild to me. We can actually see things like the ancient Farallon plate. So the Juan de Fuca plate is just the last little part sticking out of this old Farallon plate. We can see the Farallon plate all the way underneath North America because of the temperature differences. So yes, we can model all sorts of different things in different ways. And AI is a fantastic tool in general that's allowing us to expand the earthquake catalog. So there's work by Zach Ross at Caltech using AI in order to find micro earthquakes within the seismic noise that, we have all of these seismometers all around the world, but there's a lot of things that are noisy on Earth that aren't earthquakes, like, the oceans and the wind and people walking around and car noise, all of those things put energy into the ground. Using AI and using machine learning, we can tease out these tiny little signals and expand the earthquake catalog to understand even more how things are moving and over what timescales. So lots of different uses for the new technologies, as things are moving forward. That's a good question.
Good.
Thank you.
Thank you. And I have one more question. I've always thought it would be a good teaching tool and presentation tool if you could show just the bedrock, if you were able to remove all the overburden and show the tectonic setting with just the bedrock. I think people would understand what it looks like more. And I know that the overburden can show the actual movement of it. You'll see it in the overburden, but I think if you removed all the overburden and just had the bedrock, you could see the tectonic situation better, in my opinion.
Okay, that's an interesting idea. I like it.
Okay, thank you.
Anybody else? Feel free to pipe up if you got a question. I just rode for 3 hours with 2 11-year-olds, so I'm used to being peppered with questions. Hit me. Oh, question, but your mic isn't working. Okay. No pressure while you type.
Yeah.
And sorry if you hear the noise. Those said 11-year-olds are in and out with their neighborhood friends, back and forth, and the dog is going bananas.
We can't hear anything, so you're good.
Okay. I feel like I should offer up some interesting earthquake facts. Okay, there were I have to remember which states they were. Between 1974 and 1994, there were 4 states that didn't have any earthquakes. Can you guess 2 of them? Oh, there was just a 2.7 in Northern California also. Just got my alert.
I'll guess Ohio is one, just because I don't know if we've ever had one. I don't know.
Not Ohio. Ohio has earthquakes.
Crazy.
The Dakotas?
That's one. Well, one of the Dakotas, North Dakota.
Uh, Another question would be the Cascade Range. Do you have any any thoughts about, we have all of that subduction going on, of course, for the Cascade Range. How far could we expect volcanic activity to go down into Northern California? Certainly we have Shasta and Lassen, but then there's some other buttes that are farther down, and there's activity going on like right off the Oregon coast, right on the line there on the transform.
Yeah.
So can we possibly have additional volcanic action south of Shasta and Lassen?
Yes, but not from the Cascade volcanoes, not from the same source. So as the Juan de Fuca plate subducts beneath North America, once it gets to a certain depth inside the earth, to a certain temperature, really, what happens is the water that's in the minerals, it dewaters. So it comes out, and that causes the rocks above it to melt because it lowers their melting temperature. That creates the magma source that creates the Cascade volcanoes that go up into Canada all the way down through Northern California. And so that's the volcanism that's happening due to the subduction. Now, if you go into Southern California and you're looking around the Salton Sea, particularly around the southern end of the Salton Sea, you have high heat flow there as well. You have geothermal fields. That's due to the plates pulling apart that divergent boundary. We have other heat sources in California that cause volcanic activity, like Cosos at the Cosos volcano range. That's also related to kind of pulling extension rather than the subduction processes. So there are multiple reasons for the volcanic activity in California, but only the Northern California activity is related to Cascadia. So
Yeah, I was just wondering how far you think it might go into Northern California. Well, because some of those buttes they were either were active volcanoes, or maybe they're becoming active volcanoes. Because the boundary is not a straight east-west transform. It's got a little bit of a southeast trend to it. So
right.
That's why I'm thinking
the volcanoes that we have now, it's not like there's new volcanoes that are going to come about because of that system in real time, right? In our lifetime. And so the volcanoes, when we're talking like when you get down to like Lassen, Shasta, that's about as far down as you're going to get related to Cascade volcanic activity. So thank goodness we got enough problems.
Okay, it looks like
geologically.
You have the question from Singh there.
Okay, question sort of unrelated to the webinar. Oh, you read one of my papers. Okay, the age and structure of the Shayok Suture Zone in the Ladakh region of Northwest India, implications. Lived in North India for over 2 years, and in Ladakh, I love Ladakh. Don't have any sort of field knowledge. I understand the abstract. 2 questions. Could you simply explain what the goal of this paper and abstract is about? What motivated you to study and do research about this specific topic? So for my PhD, I worked in Northwest India on a fault system called the Karakoram Fault. It's very similar to the San Andreas Fault in terms of its length and its sense of motion, but very little is known about the earthquake history of the Karakoram Fault. Also, the Karakoram Fault intersects another fault called the Longmu-Ko Fault. And that's very similar, again, in the geometry to what's happening with the San Andreas Fault and the Garlock Fault. So I was interested in studying things in that area because I wanted to have a corollary for the San Andreas, and because I wanted to learn more about the Karakoram and Longmu-Ko faults to help to reduce earthquake risk in northern India. So because there's not a lot that's known, the earthquake hazard there was not well constrained. So I started working in India, and we did multiple field seasons there. We did a lot of field work. And for any kind of field work, the thing that you're really looking at that you start with is a geologic map. And so when I was looking at geologic maps of this area, in Ladakh, it's right along the border. So it's in the western syntaxis of the Himalaya. It's along the border of India, Pakistan, and China, which is a contentious boundary. And so it can be difficult to do field work there historically and at present. And so the mapping that has been done there has been largely discontinuous because of the geopolitical turmoil and because the mountains are enormous and difficult to deal with, right? K2 is in that area, second highest mountain on Earth. So not a lot of people are able to climb them to actually view the rocks. And so in the paper that particular paper, and I'll tell you how it came about. I was really upset because there were no geologic maps. And I was like, how am I going to understand this area if there's not even a base geologic map for me to look at and then put additional observations and geochronology on to understand how the fault is moving? And I'm lamenting this with my roommate and her friend. And her friend says, well, why don't you just use astrodata? And I was like, what is that? And he's like, well, it's just, we were all in this remote sensing of Mars class. He's like, it's just like the Themis data that we use to look at mineralogy on Mars, but it's for Earth. And I was like, how do I do that? And he's like, well, come over to the Mars Spaceflight Facility and we'll work on it. So I started working at the Mars Spaceflight Facility with this guy, working using astrodata, and it started this whole project. And we ended up using this type of data to look at the mineralogy across the area, because rocks are made of minerals. By looking at the mineralogy, we were able to make assumptions about the geology, which we were then able to check in the field, which helped me to make a base geologic map of the area I was interested in so that I could then start to put observations and dating methods on top of to understand how the Karakoram Fault has moved from the Miocene, or about 32 million years ago, to the present. And that's important because it helps to control the uplift of the Tibetan Plateau, which has implications for global weather circulation and rainfall patterns and those sorts of things. It's interesting too, because like on a very broad scale, if you think about India and Eurasia, right? About 50 million years ago, India slammed into Eurasia, and that caused the Himalayan mountains to go up. And what happens to all that crust in the middle? Where's it go? Is it like, there's two different models, right? Is it like a peanut butter and jelly sandwich where you squish it and everything kind of flows out the sides, like the jelly getting squished out? Or is it more like blocky and it's moving as these solid blocks? And so I wanted to explore that too. How do these big scale faults help to accommodate crust that's getting basically smushed? And so that's why I wanted to work there. And that is what that particular paper was about. So thanks for looking that up.
That is fascinating. I mean, and I love how you went around and found a whole new way to study that. That's wonderful.
You never know what's going to happen when you have a beer with friends. Just
I love using the Mars study area. I had a question that's not so much related, but it occurred to me when I was looking at the maps of the United States. Do you have any comment or know anything very much about what all is going on under Yellowstone? Because I live west of the Mississippi, so I have a feeling that everybody west of the Mississippi might be interested, according to the clickbait anyway.
right. Yellowstone is the prime candidate for clickbait. I don't worry about Yellowstone. Yellowstone's fine. It's had a lot of eruptions through time as the hotspot is stationary. The plate is moving over the hotspot. That changes where the eruptive center is. And so, unlike the way we usually think about magma, it's not like this, we think of lava on the surface as like flowing, and we were sort of taught that magma is the same thing, just underground, but it's really not. And so the chamber underneath Yellowstone is much smaller than it has been in the past, and it's pretty solid. So there's still a lot of heat flow there. There is still some, potential for magmatic activity, but it's not this super volcano that's going to explode at any time. That significant heat source is what causes all of the beautiful features, the geysers and the beautiful pools. And there are a lot of earthquakes there for multiple reasons. That's normal and expected. And Yellowstone is so well instrumented that whenever there's any kinds of change in the hydrology, changes in the seismicity, changes in the level of the land going up or down, Yellowstone kind of breathes. It gets large, it inflates and deflates, usually because of snowmelt getting into the cracks in the ground and raising it up a little. So all of these things are well studied, relatively well understood, and there are a lot of things to worry about in general and geologically, and Yellowstone is not one that I am concerned about.
Oh, that's great. I won't hesitate to go back and visit it again sometime. And I also won't worry about Arizona being covered by crap. So
Yeah.
great. Thank you.
Sure.
I love that. Sounds like he's safe. Uh, if there are any other questions, go ahead and drop them in the chat. But thank you so much, Dr. Wendy.
Of course.
When you say social media, do you like Dr. Wendy Rocks? Is that like Twitter or YouTube or how do we
Yeah,
find it?
so I am no longer active on Twitter or X. I use Blue Sky, YouTube, Instagram, LinkedIn, and TikTok. And so I tend to post for different audiences. One of the things I'm really interested in is making sure that our young folks understand that geoscience is a good career and understand why it's important to understand. So I do a lot of things on TikTok because that's where you can find a lot of younger folks, but I also put different kinds of content on YouTube. So things more like this, longer form videos, more educational videos, and yes, less like ahas. Oh, by the way, of the states, Florida is another one and Wisconsin is another one. So not a lot of earthquakes there. My video on earthquakes in Florida was basically like crickets. So I was like, okay, well, earthquakes in Florida, not a lot. On to Georgia. So anyway, I do a lot of things like that. Like, did you know?
Mhm.
So depending on what sort of content you like, I am in different places.
That's wonderful. Any last questions? Okay, well, thank you. Thank you for taking the time to present to us. Appreciate learning so much. And this will be posted on the SSPI network under resources, as well as on the YouTube page for repeat viewing. So thank you so much.
Thank you. Thanks, everybody. And I appreciate the great questions. Sorry for the shenanigans at the beginning, but got to roll with the punches, right?
Thank you.
Enjoy the rest of your weekend.